I'm Matsuo from X Fusion. Good to see you. I'm going to talk about the laser fusion. That's what we are doing. We're doing, and overview of our research. So first of all, let me introduce myself. I was studying at Osaka University, and I got PhD in science. And Laser Research Center, this research center has been leading this field of study in Japan more than 50 years. And I moved to United States, California, San Diego, and I was studying fast ignition laser fusion, high energy density, and then started X Fusion. X Fusion, we have about 2 billion yen have obtained for the fundraising, and we have about 23 people working with us. And Osaka, Hamamatsu, we have offices, and they are developing hardware. And then we have branch office in Australia. They are doing laser application. And what we want, the fusion, this has become a big topic of the day. And 3 good things about this technology: no emission. Well, this can help carbon neutral society. In the electricity generated by the fusion, laser fusion, we can develop and generate large amount of electricity, and then turn it into the thermal energy. In this process, there's no CO2 generated, and this fuel is coming from the seawater. And tritium, we have to make it as a human hands. However, deuterium, this is an infinity material. It can be found in a ocean. So what we need is a tritium, lithium, deuterium. And lithium is coming from field. So, well, in a nutshell, we can obtain the fuel, infinity number of fuel. And in Japan, we have a resource poor nation, so we have to import everything. About only 11% of resources can be obtained in Japan. And then the ocean consists of 70% of the entire planet. And now, we only have localized resources that can cause friction and the wars as well. So if we had the equal distribution of fuel, then there will be no war. Now, we're talking about decarbonization, linking with this laser fusion. And this can help us to become independent in terms of electricity and energy. So this is quite a large opportunity for us. So laser fusion, we have lots of startup company. The number is increasing, especially 2017. We have seen the jump of the number. These are the timeline showing the number of laser companies doing laser fusion. So 1998. And then we can count 1 or 2, 3 in a year. However, around this time, it just jumped. X Fusion, we started in 2021. So we are just one of them. And the right-hand side, that's just showing the line graph, showing the number of increasing number of startups doing this. So we can count about 40 of them. So, startup like us, we have to develop something quite big. However, the environment is facilitating quite nice. And 2021, large number of investment went, and that made the topics. So this 1950, the study started in 1950. So there are tokamak technology. And what we are doing is we have obtained a large amount of support money from governments. And the government is now starting discussion and arranging the laws and regulation, especially in the United Kingdom. They want to become the hub of this type of technology. And they establish some law and regulation in order to do that. And in Japan also, taking this opportunity seriously, laser fusion seriously, and they are supporting a research center like us. So as a government support, so the laser fusion technology was used to be treated as a nuclear energy, but it's not actually. And United States and the USA is having different type of view. So they don't see this laser fusion technology as a nuclear energy technology. So it's not just the government helping us with money, but they are starting from the bottom line. The regulation and law has to be changed, in order to facilitate this environment. So now, laser fusion. Laser fusion, we use laser in inertial confinement technology methods. Another one, this is another major method I just mentioned, this tokamak method. On the right-hand side, this one. This methods use plasma to heat up the plasma. They use in a magnetic field and takes long time to generate electricity. And they are now trying to swap current technology with this one. So ITER plan, yes, they have devices in South France, and other parties are also doing the technological development as well. So we have this. We decided to use this inertial confinement technology, and what we do is instantaneous reaction, and this can be repeated. So what's best about this is we can take large variation of the heat thermal. So, for instance, only one output in 1 second, or only one output in 60 seconds. So it can be changed freely. So we are now thinking about peak technology, peak electricity generation. So that can swap with the thermal generation. So, but in order to compared to tokamak, this inertial confinement is not that major, not that popular. On your right-hand side, this chart shows the output is improving. And then go back to 2018, output was quite low, as you can see. However, now why people paying attention is since 2018, in about 5 years, output became 50 times bigger. So that's why people are paying attention to this technology, especially in the United States. People are having high hope on this new technology. And there are lots of methods for laser fusion, but to achieve net gain, more than one gain, that means a lot. And now, at the moment, it's NIF in the United States and Osaka University in Japan and France, China Nuclear Technological Center, they are pushing forward with this development. And at the moment, the record number is 1.9. Tokamak methods in the United States, in the UK, the device called Q69, D69, they have a record number of gain. However, having said that, in order to start power generation, we still have lots of issues to solve. So definition for the laser commercial furnace, a power plant, gain has to be higher than 100. So we have lots of problem and issue have to solved. On your right hand side, this is the record 1.5 that summarizes the record and what they have achieved in summary. So they had used fuel 2 megajoule, and then output was more than 3.5 megajoule output. So from the ratio, transition ratio from electricity to laser used to be less than 1%. So that was no gain. But more critical problem was they could not repeat many times. The number of repeated just once in 8 hours, 2 or 3 megajoule. This doesn't mean anything. You cannot even boil a water. So thermal power plant. In the case of thermal plant, you have to at least repeat this process 10 times. So this transaction ratio has to be higher than 1. And gain, we have 1 point number as gain, but expected number to do the proper job, you need more than 100 gain.
So far, record gain is 1.9 on the during the experiment. However, that's not enough. So we need to do simulation. We need to do simulation to increase gain furthermore. I believe that gain will be gradually increasing, I think. However, we are facing technical issues such as from the conversion efficiency from electricity to current new technology. So we have to tackle these kind of issues. Otherwise, we cannot use a reactor commercially. So there are so many ways that increase gain efficiently. And Japanese experts have a kind of advantage regarding this technology. So this is the achievement of Osaka University Laser Institute. This is like a fast, quick ignition method. But with this method, on a simulation basis, as we are able to increase efficiency by 10 times in terms of gain. Left graph shows this is very complicated. I'm afraid that the axis X is a temperature of plasma, and axis Y is some formula about the. And the temperature requires 100 million to 1 billion degrees are necessary. And axis X is temperature, and when it comes to power generation, we need a certain amount of output. So in this sense, the density of plasma needs to be high, and necessary parameter is used, and a kind of formulation is used for axis Y. And when we go to the upper right, the output is high. And when we closely look at the upper right side, so for example, National Laboratory in US achieved 1.9 of gain, and record number is available here. And Fire X is at the lower left. So this is achieved by Osaka University Laser Institute. As for the output of laser fusion, the absolute value is lower than that of National Laboratory in the U.S. So, however, our achievement, Osaka University achieved only 3 joules. That means with 1/100th energy is used to achieve the similar outcome. So when we are able to establish or develop a commercial reactor with a gain of over 100, we believe that with a smaller input, we can achieve higher output going forward. Tokamak method is upper right. So this is based on the planned value. and they are now in construction. And in 2025 or after, the facility will be completed, and then 2030, this value will be achieved, it is said. And furthermore, one of other technical advantages of Japan is high power pulse, and so more than 10 times per second, and we are so able to repeat hyperpulse. So in this sense, we are leading. We are leading the research. And axis X is repetition of laser, and axis Y is pulse energy. As for axis Y, pulse energy, as I said, an energy per pulse is available here. You can see a dotted line in blue, dot in blue. So these are about large-scale laser. For example, NIF laser available in National Laboratory is upper left, and GXI is owned by Osaka University Laser Institute. So with these lasers, so we have conducted scientific validation, and energy is so huge, but repetition number is low, and in terms of NIF laser, and for both for NIF laser and our laser, output repetition is very low. And when we talk about the establishment of a commercial reactor, we need to repeat more than 10 times. Therefore, so we need to shift from the left-hand side to the right-hand side of this graph. We are very good at developing a high power pulse laser. Now, we were able to achieve the red, dot in red. And Osaka University is now researching the 100 Hertz energy, and the output is very high. Based on such technology, by accelerating our research, so we like to keep the current condition while establishing a commercial reactor. So traditional high power pulse laser, so for example, and semiconductor excitement laser is able to output more than 10 times per second. That means that the performance is increases by tenfold. There are two reasons behind that. Number one, so we applied new material, and as for usually traditional material is glass, so it is easier to output energy, but it is not so efficient. So once high power energy is output, it takes time to cool down the material. This is why we are not able to increase the number of repetition. But now, by utilizing ceramics, we can enhance the heat thermal efficiency. And furthermore, as for light source for excitement, we usually use the fluorescent light, but now, so flash lamp is white. That means there are lots of wave color included. So most of the color is eliminated or cannot be used. So laser is the most efficient light source. Therefore, by using LD, we are trying to increase efficiency. The latest laser has a high number of repetition and also high efficiency, high thermal efficiency. So we believe that we are able to achieve 10% in the end. So this is what happened in Japan. And what Exfusion is now doing is that there are many things we are doing. Now we are trying to achieve a commercial laser fusion reactor. So we need to think about the mass production of fuel or target, and furthermore, a neutron is emitted, and so blanket can catch the neutron, so that we can change neutron to energy. So this is what we are doing together with Osaka University Laser Institute and also other university. We are doing joint research. And furthermore, so we are tackling on laser control or technology. So laser control is something like when it comes to laser fusion, the fuel pellet is very small, maybe 3 millimeters in diameter or so. This tiny fuel should be targeted so accurately. This is why we need a high level of laser control. And the laser control is has common application. That's why I believe that we can apply our technology to commercial use or other industry. And what kind of development is that? So we are trying to control the spatial space and time accurately. So this is a pulse laser. So timing is very important. And once fuel is injected, so we need to emit pulse or laser. And furthermore, we need to accurately track the location of fuel so that we can accurately and surely target or hit or inject the fuel. This is what we are doing when it comes to the system. So such technology related to laser fusion, in particular laser control, there are many applied research. Of course, a laser fusion reactor is one of the applications. But other than that, so there are some applications that has realized, such as EUV light source and laser machining. And furthermore, and in order to prevent wildfire, we are able to use our technology for artificial lighting. This is one of the examples of technical application that is laser machining. So regarding this, so we are collaborating with auto manufacturer and the airplane manufacturers. High power laser is used to cut material. And laser machining is very competitive because we don't have so many consumables. We don't have to have so many consumables. For example, CFRP, so carbon material, it is very difficult to cut actually. And with laser, if we can cut this material with laser, so we can prevent the wear of a knife or.
So you can be done cheaper. To first approach, you have to intensify the laser. However, basically, laser application is to use laser with thermal. But if the heat is too intensified, it's just burning the material. It's not clean cuts. So you have to control the laser and the power of laser. So that showing here is the same output, but the cut is much, much cleaner. So now we have IP patents, and then based on that patent, we are continuing the developments. So high power laser, that's what we do. Well, and high power and cut faster and proceed faster. So that's what we want in future. Then another one application. This is to look after space debris. We are working on Australian company EOS Space Company. This picture is exactly what it says. So this is a debris collecting facility. In Australia, there's a Storabo mountain, and what they do, this cube things is a laser emitting machine, and then this is aiming at space debris, and so that they can identify exactly where these space debris are. And they have 2 lasers on the ground, and then the distance is about 1,000 kilometers. So laser has to be quite powerful because they have to travel 1,000 kilometers. And using this laser, they can apply pressure on the debris. And then when receiving laser, debris speed will be slower. And then their trajectory can be different like this. This is how they can collect and catch space debris. And I've spoken about space debris, and then some media company got the wrong idea. It's not destroying space debris, but they are identify the location and catch it. So that's how it works. So EOS Space Company, they had this business to catch space debris. However, they did not have laser development, laser capability. So that's why we are helping them. So we introduced our technology to this company, and we are now working together. This is the last slide. So that's the what's the benefit in terms of economy. So this study started in the United States. Back then, they did not take laser fusion too seriously because they did not think this will be developed overnight. Only about $400,000 or something. It's quite low. So that expectation was not something as an energy or generating energy, but some industry that can be born by this laser technology. So it's not just energy or the technology only. However, many companies can work with new technology. So that's why in the nation, many nations, especially governments, are interested and they're pushing forward this. So we are now riding on this bandwagon. So for instance, we are now looking at several trillion level of economical benefits. But the market, it was quite difficult to form a market. However, they used to penalize the company who generated space debris by using satellites. But now they can look after this space debris now. And then larger markets can be possible. So the commercialization of this technology and relating technology can reach about 4 trillion yen level economical achievement. And then this technology started from Osaka, so we have high hope on this one. That's my presentation. Thank you.